Okay, here's our quick overview of the notes for our energy unit. Energy, in our unit here, we're going to talk about what energy is and its types, how energy is transferred in a chemical reaction, and how we calculate energy change when there's a temperature change. So here we go. First of all, what is energy? Okay, so energy is the ability to do work or cause any change. All right, so if we think about that, what are some things we need to use energy for? All right, so energy is really used to make anything move or power up. So anything that runs, that has electricity, lights up, computes things, phones, iPads, cars, anything that burns gasoline, things that grow, all things we use energy for. Okay. Now there are different units that we use for energy. We have the joule, the kilojoule, and there's 1,000 joules in 1 kilojoule. And 1 joule is about the energy required to produce 1 watt for 1 second. That's not very useful for us. So a joule is about the energy in 1 small pea, like a pea pod pea. Okay. Now the non-SI unit is the calorie. Okay. Probably don't know that the most often place we see calories is in food. All right. So to give you an idea, in 1 food calorie, there's 4,180 joules. So if we were traveling to Canada, Europe, Australia, or any other rest of the world, they wouldn't report their food in calories. They would report it in kilojoules instead. So the packaging wouldn't say calories. Okay. So for example, in the United States, the Cane's box combo is 1,250 calories. So if this was being sold in a different country besides ours, what would that be in joules? Well, we take it times 4,180. That would give us 5,225,000 joules. Or in kilojoules, which you would see on the packaging, would be 5,225 kilojoules. Okay. If you want to, you can look up your own food and then multiply it by 4.18, and that would tell you what it would be in kilojoules. Now, there are 2 types of energies. There is kinetic energy and potential energy. So kinetic energy is energy that is moving or vibrating, okay? We say that kinetic energy is active energy, all right? So if it is moving or if it is doing something, if it's lighting something up, if it's causing movement, it is kinetic, okay? Because kinetic energy is about movement, the warmer we have something, the faster we can get the particles to move, and the faster they move means the more kinetic energy that they contain. So fast things have more kinetic energy than slow things. Now, we can track that through temperature. Okay? Temperature is a measure of kinetic energy. So warm things are also faster things. So warm things and fast things have more kinetic energy. Cold things, slow things have less kinetic energy. And we see this in the graphic down below. The other type of energy is potential energy. Potential energy is stored energy, okay? It's energy that is available but not being used, okay? It's energy found in structure and bonds, okay? So for example, a battery would be considered stored energy because in the structure of that battery, there's electrons being held that can be used, but it's not being used. As soon as you turn your device on and you light up your screen and the computer chip starts to work, now you're converting that into kinetic energy, okay? In the chemistry world, we call this bond energy because the actual chemical bonds, those covalent bonds, those ionic bonds we talked about, each one of those little bonds stores a tiny bit of energy. And chemists can tap into that energy to allow it to do stuff. Okay? So that bond energy is the stored energy in chemical bonds. Okay? So what kind of objects or things do we have stored energy in our everyday lives? Well, here's 4 examples I thought of. Gasoline stores energy that we can burn to drive our cars. Food is stored energy that our bodies use or anything that's alive uses to live. Batteries store energy for all of our devices. And wood and other organic materials can be stored energy for us to create fires. So 4 examples for that. Now, there are different broad categories of energy. There's moving energy, kinetic, and there's potential stored energy. So the activity we did in class was to actually sort this. So go back to that activity if you want to see that sorting. Total energy is a result of both the kinetic energy added to the potential energy, okay? So if we take the moving energy and we take the stored energy, add them together, that will give us the total energy. Now, total energy does not change, okay? We can change potential and kinetic, but total stays the same. This creates what we call as an inverse relationship. So I can have kinetic energy increase, but then potential energy has to decrease to keep total the same, okay? And vice versa, I can have potential energy increase, But then kinetic energy has to get smaller to keep total energy the same. So total energy, TE, never changes. All right? That leads us down to this idea of the law of conservation of energy. Okay? We've done the law of conservation of mass. This is a similar idea. In any chemical or physical process, total energy cannot be created nor destroyed. Okay? So we learned that energy can't be made, it can't be taken away. We can just use it that maybe it was potential. This means that mass does not turn into energy, and energy does not turn into mass. Okay? So this is a repeat of some stuff we talked about earlier this year. Okay? Now, anytime you think energy is gained or lost, we're just not tracking where it goes, where it came from, or how it's changing. All right? Most of the time, if you think energy is being created magically, what you don't realize is the energy was always there, stored as chemical bonds. And we're just unlocking that stored energy to use it. Okay, that's what gasoline does, that's what wood does. The energy is always sitting inside of them, but it takes us to light them or to burn them for us to release that energy that was stored there. Okay? As a result, chemistry converts energy. That's what chemists do with these different molecules, is we are able to convert it from being potential into kinetic and vice versa. So if you have a reaction that causes a shift in kinetic and potential energy, when bonds rearranged and they make new substances, okay? So there's a rearrangement, which means there's two possible results. When you do a rearrangement, the new compounds need more energy than the old, okay? If that's the case, if the new compounds need more energy than the old ones, they're going to steal kinetic energy, which means, in that case, kinetic energy, which is heat or temperature, will turn into potential energy, which is the bonds. Or the new compounds need less energy than the old. In that case, potential energy that was there in the bonds converts to kinetic energy into heat. Okay? So one of these two things always happen when we run chemical reactions. We either need more potential energy in bonds or less potential energy in bonds. Okay? So if we have an endothermic process, endo meaning in, thermic meaning heat, that means the energy is moving into the bonds. Okay? As a result, temperature will go down because the kinetic energy, which is warmth, is less, and potential energy stores it. Okay? It's like a savings account, right? It's like taking money that you make, you put it into a savings account. Okay? That is money that you are saving, so you don't have it to spend it. So your spending money is less, but the overall money that you have is the same. It's just stored now instead. Okay? So endothermic things will always get colder as they happen. Looking at the graphic, before the reaction, we had low potential energy, high kinetic energy. The total is here. Afterward, our potential energy goes up, kinetic energy goes down, and the total stays the same. So we see there's just a switch where in endothermic reactions, we gain potential energy, which does not help us with temperature, and we lose kinetic. Okay? Another way of looking at it is through this type of graph. Okay? So water has a bond energy that's really low, right? If we were to react it and split the water up and we want to make individual hydrogen and oxygen, so we want to go from the water side and reverse to this side, what happens is that we need to absorb energy, and these have more energy, okay? In that case, energy would be absorbed, okay? So where does it come from? Well, kinetic energy. So this process would have to get colder to go from here to here, okay? Because we're absorbing potential energy, which is stored and not usable for heat, okay? That's what brings us to cold packs, okay? So chemical cold packs, the things that we use, like if you sprain your ankle and someone breaks it open and squishes it around, yeah, they start at room temperature and they get cold in seconds, okay? It's because it's endothermic and they are drawing in that heat energy. You put it on your skin and it draws the heat away, which helps you heal, okay? The other side is an exothermic reaction where energy comes out of the bonds, all right? So exo meaning out, thermic meaning heat again. So this will cause temperature to increase as unneeded energy forms new bonds released to become kinetic energy. Okay? So this is kind of like taking money out of your savings account to go spend it, right? So maybe you saved up $1,000 and now you're going to choose to go spend that money, okay? So when you go to spend your money, what happens is you have to take it from the savings place where it's not spendable to your checking account where you can spend it, all right? In this case, energy goes out of the system and becomes available so it warms things up. We notice how our potential energy and our kinetic energy are opposites here. Not surprisingly, our energy diagram would be opposite also for exothermic. So in this case, if you start with the hydrogen and oxygen and they turn into water, they're going to release energy. And when they release energy, it's going to warm up, okay? So where does the excess energy go? To kinetic, all right? So endothermic reactions, they get colder and they steal from kinetic energy. Exothermic reactions get warmer and they give back to kinetic energy, okay? And this is how hot packs work. So a hot pack does the exact opposite. When we open up those disposable hot packs, they undergo a reaction that has too much extra energy and it releases it out for us to warm up our hands, okay? This is when we did a quiz, okay? So how do we find heat energy change when temperature changes, okay? We need to know three things, okay? First, the mass of the substance, starting at any temperatures, and type of substance, or we call it heat capacity. That's the three things we need to know to be able to find energy change, okay? Every substance in the world has its own heat capacity or its ability to absorb heat and hold on to it, right? So notice how we have a whole list of them. Notice how water down here is really high, 4, where most of these are less than 1. Our hydrogen's super high too, okay? So water has a really high capacity to hold heat energy, okay? So let's do a little concept check. Things with high heat capacity take a lot of energy to warm them up. Things with low specific heat capacity warm up with little energy, okay? Secondary part, might want to draw a line here. Things with high heat capacity give away a lot of energy when they cool down. Things with low heat capacity give away a little energy when they cool down, okay? That's why water is good for cooking and burn you when you're hot, because it has a high heat capacity, which means when it changes temperature, it can give away a lot of energy and take in a lot of energy, okay? Now, to calculate that, we end up with an equation. It looks kind of fancy. E, meaning energy, is equal to M, which is the mass, times C, well, that's the heat capacity we have to look up, times the final temperature minus the initial temperature, okay? So we need to know the change in temperature, okay? If we have a negative energy, that means it's being released and it's going to get colder. If we have a positive energy, that means it's absorbed and it's going to get warmer. Okay. So let's do a solving thing. Okay. What's the energy change for water when 50 grams of it goes from 100 degrees Celsius to 60 degrees Celsius? Okay. So we see that energy is going to be going out because it cools down, starts at 100, ends at 50. Okay. So we just use our equation. Mass times the heat capacity for water times the final temperature minus the initial temperature, and we get a negative 8,360 joules of energy, okay? We use a negative sign here that tells us that energy is being lost by the water. It's releasing that energy out, okay? Now, let's flip it around. Let's solve for heat capacity. So we have 1682 joules of energy into 25 grams of metal. It warms up from 50 to 125 degrees Celsius. What's the heat capacity of this metal? So now we take our equation and we rearrange it and we solve for the heat capacity. So we have energy divided by the mass times temperature minus initial, okay? And if we do that, we get 0.897 joules per gram degree Celsius. So we come over here and look, well, what is 0.897? Oh, that's aluminum, okay? So we're talking about aluminum metal here. Now, last one, what if we need to solve for mass? We have 1,500 joules of energy to warm up ethanol. What's its mass? So again, we can rearrange this equation to look like this. Okay, so now we've seen all three rearrangements to solve for either energy, mass, or heat capacity. And we plug our numbers in and we get 12.3 grams. So then how does heat flow? Now that we know about energy change, what happens? Well, when two objects come together, heat always flows from high temp to low temp. So we see this flowing of heat energy from high to low. Heat always moves from high to low all the time. It's going to continue to happen until they have the equal temperatures, which we call equilibrium. So they're the same temperature, okay? This is no different than our hands or anything. If I touch something cold, the heat energy is going to come out of my hand to warm up that object, okay? If I touch something hot, it's going to be the exact opposite, okay? Which means that energy lost by one object in an insulated container will always equal the energy gained by another. This is called our first law of thermodynamics. So energy gained by one thing has to equal energy lost by another thing, Okay, so how do we measure it? Well, we do something called calorimetry. Okay, it's a quantitative measure of heat changes. Okay, and we're going to do this actually in class. If we can measure the energy change for one thing, we can find the energy change of the other thing. Okay, so if I place hot copper metal into 50 grams of water that's at 20 degrees Celsius, the copper warms up the water to 45 degrees Celsius. What's the energy gain for the water? Okay, so here's our heat capacity of water. What's the energy loss for the copper? Let's answer them both. All we would do here is actually solve for the energy change for the water. Okay, so the 50 grams of water, we see that it started at 20 and to 45. So we'd find the energy change for water, and the energy loss for copper would be the same number. Okay, so if we solve this, we take 50 times 4.18 times 25 is 20 minus 45. That number would be the same, just the opposite sign for copper. That's our calorimetry practice.